the open source Kythe project. Kythe aims to establish open data formats and protocols for interoperable developer tools. And I'll be explaining to you what that means in the following way. First, I'll give you an introduction to the project, give you an overview of how we affect the project, talk about testing a little bit. And this is interesting because, as it turns out, because of the way the components of Kythe fit together, we're able to abstract testing from particular programming languages. Then I'll talk about how we do cross-language support between protocol buffers and interface description language and any generic programming language, and then conclude. So first, here's the problem that you generally are trying to solve when you're doing programming language tooling. You have something you want to do, and you have a language that you want to do it to. But you don't really want to re-implement that thing for every possible language that you use. So at Google, we use a whole bunch of different languages, right? And we have a whole bunch of different tools. And we don't have the bandwidth to implement the cross product of those things. So you start to look for abstractions, right? You say, well, maybe I can write an analysis that works on languages that are mostly compatible to C++, like C. Maybe you can do cross-references as long as your language is supported by the Clang front end. Maybe you can generate documentation provided you can write regexps for languages that have curly braces in them. Or maybe you can do code review or code search tools based on programs that are stored in plain text, which kinds of leaves languages like Squeak, which are image-based in the lurch. But really, that's not the whole problem, right? You have some kind of source code repository that you're talking to. You're maybe using Git, Subversion, CVS, your company filer, your local disk, or you're just pulling code off of someone's port 80, right? You're using different build systems. You're using CMake, GMake, Bazel, Maven, a bunch of shell scripts, and maybe Ant. And you have some code generators involved too, protocol buffers, Thrift, Captain Proto, Yak, Antler, or maybe the JNI. And your tools have to understand all of these things to be maximally effective. So what we propose with Kythe is this sort of classic hourglass thing, right? Where you have support for some common interchange format that you implement for all of the languages on the input side, and all of your tools consume it, right? But it's not just the programming languages that you want support for. It's your build systems, it's your other tools. And the tools that you want to consume this data are your cross-reference servers, your editors, your documentation generators. This is slightly different from extant technologies like the language server protocol, in that we're concerned about the semantics of the intermediate representation here, not so much about the protocol that the tools use to communicate with it. While we do provide some protocols, we're really interested in how we represent programs and how we can represent the semantics of the programs at a deeper level. So how do we do this? How do we build this intermediate format? We've factored the idea of analyzing source code into two major phases. First, we start with the build system and then run it through a process we call extraction, where we pull all of the information we want, or all the information we need to do semantic analysis over source code into build data, which I'll explain shortly. Here, you can stop and pull the build data into your existing analyses and not have to worry about repositories or build systems. If you want to keep going, though, we provide an indexing step that takes this build data and produces our intermediate representation that you can then feed into a database and then read with other tools. What does the build data look like, right? So after we start with the build system, we produce something. This build data has an interesting property in that it's hermetic. It contains every dependency your compiler needs to do semantic analysis. It also gives files identifiers that can be used to locate them in those repositories. So this is where we abstract away the necessity to understand your build system or your Subversion instance. Together, this allows for the distribution of analysis tasks in the following way. You might have a bunch of machines that are allowed to touch your source code, right? And a bunch of machines that are allowed to do analysis. And these aren't the same set of machines because source code is precious, right? So once you build your database of compilations, you can pass those to your cluster of machines that are allowed to do analysis on them. That cluster no longer needs access to the original repositories. In the same way, you can pass those compilation units to someone else entirely and have them do analysis on them. Because of these names that we associate with the build data and with all of the files in them, we can go back and look at where they came from in the original repositories without actually having to touch those repositories in the first place. This is what one of these compilation units looks like for C++. It has all of the transitive closure of the headers that you need to compile a particular source file, as well as the arguments you need to invoke the compiler on them, and the source file for the particular compilation action. For Java, it looks fairly similar in that we have your Java source file to build a particular jar. And then we also have all of your dependency jars included into this single file. But we do some special stuff to them. We don't really need the bytecode to analyze, or the bytecode of your dependencies to analyze a particular Java project. We just need the public signatures inside those jars. So we eliminate the bytecode and just store public signatures and any details that are public in the class files. So once you have these things, you've taken your build system, you've taken your repository, you've built a whole bunch of these compilation units that describe all of the build actions in your project. What do you do with them to produce cross-references, for example? You produce our interchange format. The interchange format is a big directed graph. All programs are represented with nodes, which are just named maps from strings to bytes, and we'll call these facts sometimes. So a node might have a fact on it that says its kind is record. And these names, so the name of a fact, for example, is namespace. So we have the Kythe node, or the Kythe node in this namespace is sort of the root. You can define your own fact names and do your own analyses and put them in the database. Then we have edges between nodes that are triples of source names, labels, and then target names. In our graph, we have nodes that represent both semantic information and syntactic information. So an example of semantic information is the thing I just showed you, right? We have a node in the graph that represents some records. So it came from a struct or a class in Java. And it says, this is a record, this has some unique name. But we'll also have a representation of the binding site in your source code that caused that record to come into being. So somewhere you will utter class C. We have a node in our graph that says, this span of text in a source file gives rise to this node. And the way that we represent that is with an edge between the syntactic node and the semantic node, and we call that edge defines binding. We sometimes call these spans of text anchors, just like in HTML you have anchors. So as it turns out, in one of these graphs, we store information about a whole bunch of different programs at once. So naming becomes very important, right? You don't want two things from two separate programs to have the same name because they're indistinguishable. So to start out, we have structured names for nodes. There are, about 5 fields in one of these structures. What they're actually called are unimportant. What is important, though, is that some of these fields are fixed, right? Well, we have one field, for example, that says this node came from this particular programming language. But the indexers, the things that take the compilation units and build Kythe interchange format from it, are left to build node IDs for themselves. There are some maxims that we give people to help them come up with good names. For example, things that are the same should be given the same name. This has important implications because, for example, the graph can get very, very big. And if you have unique names for things that aren't unique, say the representation of a type, then you're not going to be able to store the graph. So we say, when you have a representation for a type, try to hash cons it, right? You should have one type for the type constructor for a pointer. You should have one type for the built-in void. And you should also have one representation of the type for void star, which is the type application of void to pointer. On the other hand, it's important that things that are different be given different names. And this can sometimes be surprising. For example, users like to see that different forward declarations of a function in C++ are different things in the graph. So, for example, they can ask, where are all of the forward declarations of this thing? If we merge them all into the same node, we would no longer be able to distinguish them. It also turns out that writing down the qualified name of something as the node's name is insufficient, right? The canonical example is int main in C++. Because we have a whole bunch of programs stored in the graph, if we had only one name for int main, we would no longer be able to distinguish them, and we would no longer be able to tell those programs apart. As it turns out, in a big multi-program graph, even qualified names in Java are not enough to distinguish between different program artifacts. So for Java, we name things after their qualified name plus a hash of the structure of those classes. So once you get your names right, and that's probably the hardest part of integrating with the system, you have to start describing the relationships and the particular nodes that you've generated. So what we do is we provide a base set of nodes and edges in the Kythe schema. We also provide rules for naming certain kinds of nodes, right? So if indexers are allowed to come up with their own names for things, and really they are, and we say this should be a part of the implementation of the indexer and it shouldn't be public, you have to be able to get in the graph somehow. You need to be able to address your objects. The easiest thing to address is a file. You can just ask the system, show me all of the things that are declared in this particular source file. And you can do that because we dictate how source files are supposed to be named. The schema is extensible. So I mentioned that identifiers for edges and identifiers for facts are sort of path structured. So stuff under the Kythe namespace is ours, and we dictate how that's supposed to be used. But you can use your own paths, and you can propose to add them to the schema. So this leads to the maxim that you should be conservative in what you send to us, but be liberal in what you accept. In that, when you talk to Kythe, some data may be missing, right? Some people just might not be able to produce data. Maybe they're analyzing a dynamic programming language. There may be more data than you can understand. This means that some people might be writing their own analyses under their own paths. Some people might do the wrong thing, and that's okay. You should be robust. And in the end, Kythe is not a formal system. It's meant to be a scalable system, though, that you can use to drive stronger analyses. For example, you can ask our system, show me where all the references of where a particular thing is. You can pull down the compilation units that led to those references being generated, and then run your language-specific analysis over them. It's also meant to be extensible in the sense that if you start with a really, really simple implementation of an indexer, like you write something for Python that can only look at local references in a single file, you can improve on that indexer without having to change the schema, without having to change the tools that consume the intermediate format, by just emitting more data. So here's an example of a section from the schema, and it's not really important what's written here. I'm just showing you the general layout of it. We'll give you, for each artifact, an informal description of it. So this is for that defines binding edge, and it says sort of like where you can expect to see this thing come up, from what kinds of edges, or from what kinds of nodes it should come, like maybe syntax to semantic nodes. And then we'll give you some checked examples about how this thing is used in different programming languages. And the languages that we have in the schema document, for examples, are C++, Go, and Java. So with all of that in mind, so we start from your build system, we build the compilation units, we index the compilation units, we get a bunch of graph artifacts. How can we actually connect a project, let's say based in CMake, to a web browser to get cross-references? So the first thing that we do is we run extraction on it. CMake has this nice property where you can ask it to build a compilation database, which is a big JSON file that contains main source files, working directories, and invocation arguments for your compiler. This differs critically from a representation of compilation units because it doesn't contain the source text. So you still have to have a local checkout of your source code in order to use one of these compilation databases. So after you run it through the extractor, you have this whole bunch of hermetic build data that you can use to pass to your indexer. The indexers construct data in the interchange format. And remember, this is just a big graph of nodes and edges. And we'll dump all that information into something that we've titled the graph store, which is really just a big on-disk database. Services then use the graph to answer queries. They do code browsing, code review, documentation generation. And you can have different services in different RPCs to talk to the same store. This design is known to scale. So what we consider a small data set is what we have powering Chromium code search. And actually what's running is the second version of this system. This is the third version of the system that we've built. This data set has about 36,000 C++ compilations that generate about 50 gigabytes of serving data. Our internal instance of code search is much larger. It runs daily on over 100 million lines of code in a bunch of different programming languages. And other internal tools actually do make use of this build data. So they do get off the train early and pull down compilation units and run their stronger analysis to do language-specific things. Now, I lied a little earlier where I said that things talk to the graph store directly. That's too slow because the graph is just too big. and the queries are too complicated. So for each client, so say for a code search client, or something that follows cross-references, we go through a denormalization process. So we pre-bake some queries over the graph. For example, we will pre-bake a source file with all of the links in it for definitions and references, so that when users go to query a file, we are able to give it to them right away. One of the more interesting steps that we go through during denormalization is the generation of clusters for definitionally related nodes. And what does that actually mean in practice? Well, as it turns out, users like to think of things like forward declarations as distinct and as the same thing in different contexts, right? Imagine that you're asking for all of the call sites of a function f, and you have some forward declaration of f that's some .cc file c, or some source file c, and the implementation of f, the full definition of it, that other source file c. If a user asks for the call graph for f, and they only see calls to this, or only see calls to this, that user will be upset, and rightly so. So what we do is we have canonical ways to say that certain nodes are associated with one another. So we say that this forward declaration is completed by this definition. When we have those relationships in the graph, we can build this cluster around them and blame calls to this on the cluster instead of on each individual node. Now we maintain that relationship, right? We can still say to the user, oh, here are all the calls to this particular thing, or all of the calls to this particular thing. But we're able to give them the merge site, or the merge calls very quickly. We have support in our open source project for a bunch of different languages already, and we keep adding more. We have great support for C++, Go, and Java. We have a nascent indexer for Haskell, for Rust, and for TypeScript. And internally, we have support for a bunch of other languages. So I'd like to talk to you about testing a little bit, because this turns out to be kind of interesting. At a high level, if you even go higher than in the first couple of slides, you can think of our system as something that takes in source text, passes it through this extractor composed with an indexer, and produces graph artifacts. How would you actually test one of these things? In the earlier revisions of the software, we would write tests in each programming language that we built an indexer for. And these tests all kind of follow the same pattern. You have to find something in a source file, like the declaration of a function. You have to identify what parts of the graph that should generate. And you should make sure that you disregard other stuff in the graph that you're not interested in, because otherwise, if you do that thing earlier that I mentioned, where you can progressively improve your indexer by omitting more data, you don't want a better indexer to violate your previous test. This really is a search problem. So let's cast it that way. Let's say we'll build a generic component that can look at the source text, can kind of clamp in here, and can look for various graph artifacts based on user-provided expressions, not in particular programming languages defined by source text, but by a language defined by this testing tool. So we call this the verifier. And a test that is so instrumented looks like this. Here's our function declaration. And we want to make sure that it produces a graph that looks like this. So progressively, we'll say there's something that is printed as f, like the token f, should exist on the following non-assertion line. So here's an f, and this is looking for it. We want an edge in the graph. This defines binding edge that connects to something else that we don't know about yet, some function. So here's that node. It's an anchor node, and it has some start and end location, which are offsets in this source file. And we have an edge that we specified that connects to something else we don't know about here. But we're going to call it function f in the scope of the test. We'll say that this function has the proper node kind associated with it. So we're looking for something at the end of that edge, like this. So how we actually solve this is by lowering this test to a tiny constraint language. What's actually printed here isn't so interesting. It's just to show that, yes, we do some lowering. And we produce logical variables or existential variables for each of these things that we're searching for. So we have a variable that represents the syntactic node for f. Remember, the anchor in the source text. And that shows up where we check to see that it exists on an edge, and we check to see that it has the right range. And then we also have a variable for the function f, and we check to see that it has the right node kind. When we go to actually process this test case, we run it through a really naive, but still sufficient for our purposes, logical solver. So here's the graph that I showed you earlier, and we'll walk through what the solver actually has to do. So the first thing that it's going to do is try to find an assignment for this variable. And it gets lucky, and it says, well, yeah, we'll say this is what we'll assign to @f, which, remember, is the syntactic representation of the function's binding site. And it has the right start and end locations, and it has the right kind. And it also has the right edge here. Because it has this edge, and because it has this source, it can try to unify or assign this function variable to this node. And as it turns out, it gets it right. If it gets it wrong, it does kind of the obvious, or maybe not so obvious, backtracking thing, where it keeps trying to find satisfying assignments for all of the logical variables in your test. If it can, then the test passes. If it can't, then the test fails. This is what the output of this actually looks like. And my point in showing this to you now is that you can have a lot more stuff in the graph than what you're actually interested in. But the testing framework allows you to draw a box just around the stuff that interests you. And here, this is where we've unified the existential variable for function f. And here's where we've unified the variable for the anchor. So with all of this in place, we're actually able to do cross-language support in a really easy way. This is something that a lot of these tools don't actually support. And we're able to get away with it because we have this consistent representation and reification of syntax in the graph. So I mentioned earlier that in our data store, we have graph nodes and edges for lots of different programs in lots of different programming languages. But they're all little islands because one of the things that we've said is, well, one indexer isn't allowed to know how to utter the name of another indexer's nodes. This actually comes from some experience because, as it turns out, in previous versions of our tool, people were writing queries against the graph that had special knowledge of, say, how the C++ indexer generated names. This kind of ossified an interface that should never have been an interface in the first place and made it harder for us to make changes without breaking people. So now we say, well, you're not allowed to do that at all. And furthermore, we're going to hash all of our names so you can't even try. Anyway, the problem with this approach is that sometimes users think that things that are actually distinct are the same. In the same way that users sometimes want to see forward declarations and definitions to be the same thing. They also want to see things written in an IDL, like protocol buffers, which are used extensively at Google, with the code that they generate. For example, you might write in your interface definition language the definition of some message type, M. This generates implementations of the message type in a whole bunch of programming languages. For example, Java at the top right here, and C++ at the bottom right. As it turns out, users really want to see all of these things as the same thing, right? They want to see them all unified in the same cluster, like we talked about before. It's still important to maintain the differences. Users might want to slice the program only by a particular programming language. But in the general case, you really want to say, where is message M used across the whole code base? How can I refactor message M without breaking anyone in any language? Can I remove a field? Can I rename a field? Without knowing how to utter the name of M in these programming languages, though, how do we draw in those edges that tell us to draw this cluster around them? It turns out that we're allowed to do this without violating our rules. Let's look at how the process works. So first, we have our source code in the protocol buffer IDL. This just defines the message type. And because this is a programming language, just like any other programming language, there's an extractor and an indexer for it that takes in that source code and produces a graph artifact. So we have this representation of the message type in the graph. It also has a name It has some signature that the protocol buffer indexer generates. The protocol buffer compiler also generates Java source, for example, the implementation of class M. But we have instrumented, and the code is there, the code is public, the protocol buffer compiler to also produce this kind of sidecar file. It's a metadata file that says, in the Java source that I just generated, this token M is associated with this signature. The protocol buffer compiler and indexer are in on it with one another. This is allowed, but it's just contrary to the direction things normally work in, right? Usually the indexer is completely subservient to the compiler. But here, the indexer dictates to the protocol buffer compiler, here is how names are generated. It would be unwise to make the Java indexer understand how these names are generated, because it would mean that we introduce a strong coupling between two components that previously were uncoupled. It would also mean that for every new code generator, we would have to implement special support in every language that the code was generated into. So we take this metadata file, which again is just a bunch of source text ranges that link up to addresses in the Kythe graph, and pass it through the Java extractor and indexer. And we'll produce a representation of the Java node for public class M. But during indexing, we have associated this metadata file with the Java source file. So the indexer knows to look for this M. When it sees the M, it knows to paint in that additional generates edge. And this edge, we know internally during our denormalization process, should cause one of these clusters to be built. So now we can say to users, anytime you see a reference to the protocol buffer message M, or anytime you see a reference to the generated code for M, consider those things to be the same thing. So now users can ask, show me everything that uses this cluster. Or users can ask, show me everything that just uses this node, or just uses this node. Show me anything, or show me everything that I would need to touch to change the definition of message M. Now, one last thing. The one problem that we've run into and solved is that this metadata file is a new, weird binary thing that has to be passed around with the rest of your code, right? The build system needs to understand it. And sometimes writing build system support can be complicated. Build systems are very smart. They'll do things like, for C++, look at all of the includes in your transitive closure of includes or in your source files, and only allow the compiler to touch those that you've actually included or declared that you've included by doing regex-based parsing over your source files. This doesn't work if you try to say, attach a metadata file to your source file, because it's not an official include. And you can't just use an include because it's a binary file and the regex parser will fall over. So let's think of a simple code generator that, say, takes a file that just has a bunch of names in it and then generates void functions for them. For that, it might build this implementation file of a function that just is called test. It's not a very useful code generator, but it's a useful example because it doesn't do anything interesting. This generated code file will include a public interface that is also generated. And that looks like this. For C++, this is how we associate metadata with a particular compilation. We have a special preprocessor definition that we define during indexing. And the reason that we do this is it allows us to do more expensive things when we're running the indexer than when we're doing the compilation. And as it turns out, when you have a whole bunch of different protocol buffers in your file, this really has significance. We have this pragma, which attaches the metadata file to the current source file. So this is how we say to the indexer, when you're looking at different definitions in this source code, also make sure you look for these special ranges to generate the additional generates edges. And then we have a regular include. And this is there to satisfy the build system. The one final thing we do, though, is we have to make our binary metadata look like just plain text. Otherwise, include scanners get upset with us. So we base 64 it. This looks like an ordinary header file that just has a comment in it. The indexer's in on the game, and it knows that it can just decode this to a metadata record. This just says test base 64 string, so there's no use typing it. But when the header scanner goes through, everything's okay. And it understands already that header files are dependencies, or the header file that's part of a generated code dependency should be passed to all of the dependents of that thing. So everywhere that the generated code is used, so too is the metadata available. We've had 2 groups already internal to the company that have built custom support for their code generators based on this thing, where they didn't actually contact us first. They just went and did it, which is really cool. So anyone, internal, external, can just pick this up, build support for their bespoke code generators, and not have to change Kythe, and not have to change the indexers, and not have to change the compilers or the build systems. They just produce this metadata, which is open and fully specified. So, to conclude, Kythe is a set of open data formats and protocols for building interoperable developer tools. We give you this graph schema that defines a common vocabulary, but allows arbitrary extensions to it. So this common vocabulary is actually really important. And in fact, with the verifier test language, that constraint language, it becomes a way to talk to one another about the shape of a graph, right? Instead of walking to a whiteboard and drawing lots of boxes and arrows and things, you can write down in a really simple, concise, and understandable way what you expect to get out of a particular program in our interchange format. You don't have to adopt the whole system for the system to be useful. If we have support for your build system, you can pull out the compilation units and use them to drive your special analyses. And we're running this stuff in production every day over a very, very large code base. And the more important thing is that our users report that the cross-references that we generate are their favorite internal developer feature. So I will leave you with links to the project and to our mailing list. And please visit and ask any questions there, or ask any questions now.
Thank you for your talk. A quick question. If I understood, for your system to work correctly, it relies on being able to identify the things which are literally the same, to make sure you don't duplicate it, because then you'll say that you referred to it twice. In practice, how does it work with languages which have undecidable subtyping? So when the notion of equivalence is commonly defined as A is a subtype of B and B is a subtype of A. If one of the things happens to be undecidable, it's not clear how you join them.
If A is a subtype of B and B is a subtype of A, then isn't A equal to B?
Yeah. So, but if subtyping is undecidable, then well, equality for such languages would be undecidable.
So for those, we can actually represent we have a representation of the subtype relationship. So we can use that to unify things together. Even if they're undecidable from the theoretic perspective, we can still record in the graph that people have established those relationships, and then use that establishment to build the clusters and give people useful cross-references. So
if I got you right, you're approximating subtyping, but something which is decidable, but maybe less precise.
I'm sorry, I didn't catch that last part.
You're approximating subtyping with something which is decidable, but maybe less precise.
Exactly, yeah. So we don't produce representations of programs that you can compile down, or we don't produce representations of programs that you can type check. We produce glosses of programs. You can think of it that way. Like, it's a common interchange format that is lossy, but is still useful enough to supply a whole bunch of different developer tools with the information they need to be useful.
Thank you.
Thanks.
Did I understand correctly that you built your own graph database? And if so, how is it different from RDF-style graph databases?
So we have not found an RDF-style graph database that can deal with our data. The database and the denormalized the representation of the graph is built in open source world on top of LevelDB. And then we have another LevelDB based implementation of our denormalization pipeline. That's all at Kythe.io. If you go to, our stuff is up on GitHub if you want to play with it.
And I noticed your test spec thing was, in a way, quite similar to the query languages often used for graph databases. Was it an inspiration, or is it like independently?
So it was, no, I agree. It is very similar to graph queries. It was independently developed. It's not a new groundbreaking theoretical development. It's just something that we said, like, here's the kind of data that we have. What is a concise way of expressing constraints over it? There's like a how-to up on our website that describes the language in full. There's a bunch of neat little things in it, like you can have groups of rules that are negated and other things like that. But in the end, we've tried as hard as possible to keep it simple, keep it small, and keep it focused on testing. I mean, the best thing about a programming language is the constraints that it puts on you, right? The stronger a language is, the less you can do in it.
So following up with a question that I asked before, have you had any examples where your approximation was too crude and the information which user was getting back, let's say all the call sites, was too imprecise and not informative? And did you have to tweak? How do you, simplify the data and your loss? How much information do you lose?
Let's see. Yes. There are, plenty of examples when you're developing these things, and sometimes it's hard until you get a bug report in or until you're browsing around. So for Java, for example, it turns out that one of the important properties of naming is that when you're generating a name internal to a source file, it has to be the same as when you're generating a name external to the source file. And because we do this trick where we suck out all of the bytecode and we suck out all of the private members from a class before putting into the compilation unit, it's imperative that the hashes that we build of those classes don't include details about those things. So one of the problems that we had was we were not properly unifying names external and internal to source because the hashes that we were building included some private implementation data, which turned out to be some flags in the bytecode that got eliminated.
Thank you.